Thank you all for coming. Wow, this is an amazing turnout. So we have an awesome panel here today to discuss the science behind Interstellar, some of the cutting-edge research in astrophysics and planetary sciences that underlies the film. So without further ado, let's kick off the panel, and I'll introduce our moderator, George Musser, currently a Knight Science Journalism Fellow here at MIT. Also a contributing editor to Scientific American and the author of The Idiot's Guide to String Theory.
So let me just emphasize that this is a spoiler-minimized event. A couple of us here have actually seen the film. I don't know how many people have actually seen it already. Okay, when you guys ask questions during Q&A in about half an hour, ask it in a way that will not spoil it for the rest of the people. So just tailor your question. I'll give a little summary of the film that's enough to get us through the discussion that we'll have. But the real excuse for us to be up here and all these amazing researchers is to hear about some of the great science that's really inspired by the film in astrophysics. So we're not here to pick apart the film or say, Hollywood, you did that wrong, or whatever. We all know that's the case in films. We're here anyone know a completely accurate film about science? Probably very boring to watch. So we're here to really pick apart science that's inspired by it. Anyway, here in a nutshell is what Interstellar is about. You've probably gotten this already in reviews of the film. Earth. Earth is in a bad way. Environmental collapse. So a kind of rump NASA creates a space program to go out and find another home for humanity among the stars. Another planet somewhere outside our solar system. Now, it's outside our solar system, which presents a problem of distance, which the filmmakers conveniently get around by using a wormhole to get us out to that other planet. The Rump Space Agency, actually I think it's called NASA, sends advanced parties of astronauts out there to kind of scout out different planets and see, is that good, which planet would be the best place to relocate the human species. And then the film follows kind of a follow-up mission that's going to be the one to select which of those planets we're going to end up on. So one final detail you need to know about the movie is that all these planets are conveniently or inconveniently, depending on your perspective, located around a black hole. So probably inconveniently for the habitability of the planet, which we'll be talking about, but quite conveniently for the narrative and the plot. So there's a lot we're not going to get into today. A lot of suspension of disbelief that you have to have. We're not going to really get into the environmental side of the film, for example. We're really just going to springboard straight off into astrophysics. So the three things we're going to talk about are wormholes, black holes, and planets, exoplanets, extrasolar planets, planets beyond our solar system. So we have here two experts on that very topic. So what I'll do, just in terms of the format here, we're going to have a round of questions, several rounds of questions, and then we'll open it up for general discussion. So one thing that struck me about the film was the diversity of the planets that are presented. So this man here has actually discovered some of those planets out there that we already know about. Zach Thompson. And maybe ones we won't know about, you'll discover soon. And you've done observations to characterize some of the other planets that have been known and trying to figure out what they're like. And he's a postdoc here at MIT. So Zach, is it true to life to have such a diversity of planets that were presented in the film?
Yes. Well, so I haven't seen the film yet, so I'm not sure. But I'm guessing yes. It would be hard for the film to match the actual diversity of planets that we do see in the universe. So, just for a little bit of context, our solar system is very small compared to the galaxy. There are billions and millions of stars in our galaxy alone, but they're all extremely, extremely far away. And so it's just hard to find planets around other stars. But people started looking. I think the first people looking for planets, everybody told them they were crazy because they said there's no way you're going to find anything. But then they did. They started finding planets. And the first planet discovered was, I think, one of these really weird ones. It was a planet that's the size of Jupiter, but it's orbiting around a star like the sun once every 3.5 days. So Earth goes around the sun once per year. Jupiter goes around the sun 11 years? Is that the period? I should know my numbers a little bit better before I set up a panel.
You've already passed your qualifying.
Exactly, yeah. But this planet orbits its star once every 3.5 days. And so that means it's extremely, extremely close to its star. So if you look at the star in the star would take up that much of the sky, pretty much. So it's just a really weird world. And since that first planet, I think we've just been delighted by the continuous diversity of planets that we've discovered. And so I did check one number, which was the number of planets that we now know of, or approximate number. Some of these we're not sure of, but approximately there are 4,875 planets known outside our solar system. And so most of these, they're just sketches of planets. We don't really know. But from what we've seen, there's just weird stuff. There are things that are kind of like the Earth. There are things that are rocky. We've discovered planets that we think are rocky, like the Earth. We've discovered other planets that are about the same mass as the Earth, but way bigger. So puffier, like puffy planets, planets that are like our own planet, but just have this huge envelope of probably hydrogen gas around them. And we have no idea how a planet like that forms or survives, but it exists out there in the universe, so we have to deal with it now. And then kind of everything in between. So there's a lot left for us to figure out what's going on there.
Cool. So as I said, one of the characteristics of the planets that are in the film is that they're near a black hole. And so we need to know whether that was such a good idea or not to look for planets near a black hole. And we have a black hole expert here, Leah Corrales, who's also a postdoc at MIT. And she's worked on black hole, she's actually worked on a lot of things, but black hole accretion disks is something that you've worked on. So the question I have for you, Leah, is tell us a little bit about the environment that these planets would probably be embedded in.
Okay, so can everyone hear me if I speak at this volume? Yes. Okay, great. So I'm going to backtrack for 1 second and say you probably think of a black hole as something that doesn't emit light. That's why it's called a black hole, right? Because light can't escape it. But if you have material that's falling into the black hole, then that material, as it's spiraling in, forms what we call an accretion disk. So an accretion disk is a disk of material. It gets really hot. It's a plasma. Electrons are stripped from the atoms, and you get something that lights up very bright. So that's how we're actually able to observe and know that there are a lot of black holes in our universe. So this accretion disk can actually get very hot. We're talking 10 million degrees or so, and it's going to emit a lot of UV and X-ray light. So it's extremely high energy. There can be magnetic fields that then cause these huge jets to come out. So these jets are material that come out of the accretion disk. They can go very, very far, and it really just depends on the size of your black hole. But it's a very hostile environment. So I think it's very interesting that they put these planets around the black hole. So it's definitely something to think about.
Cool, thanks. So we also have another exoplanet expert here, Sarah Rugheimer, and she's just finishing up her PhD at Harvard-Smithsonian Center for Astrophysics. Now, I have a rule whenever someone's finishing up their PhD, never ask how much longer they need. It's a question you do not want to get, but I had to break the rule for the purposes of today's event, and she's defending in January, so yay! And her specialty is modeling exosolar planets and trying to ascertain could they be habitable or even inhabited. So, Sarah, when you hear about this kind of environment around a black hole, what's your reaction? I mean, what do you think is going to happen to that world?
I think it's a bit concerning, if for no other reason. So when we normally think of habitable planets or worlds like Earth, we're thinking of stars that are maybe a bit hotter than our own sun or a bit cooler. So our sun is 5,778 Kelvin. You know, the hottest stars that we model for habitability are around 7,000 Kelvin, and the coolest stars can go, pretty cool, around 2,000 Kelvin. But these, accretion disks are glowing at much shorter wavelengths, and so my thesis actually revolves around studying the impact of UV light on Earth-like planet atmospheres and other atmospheres. And I think that, it depends, of course, on the distance to the star, but the amount of high-energy radiation you're going to be getting from these types of objects, these accretion disks, are going to make it very difficult to retain an atmosphere or have chemistry that's going to be stable on the surface of that planet. So That would be my main concern from a habitability perspective, is just the amount of high energy. And when we think of, with UV light on Earth and in Earth's early history, before we had a protective ozone layer, the ozone layer has only been around for, say around 2 billion years after the rise of oxygen, we started to have some ozone. Before that, we had more UV reaching the surface. But even so, a lot of that UV radiation can also be helpful for some origin of life reactions. But all the UV radiation below about 120 nanometers is destructive. So this is where I would worry about things where you have tons of X-rays and really high energy. Might be, not the best place to seed your new civilization. But I think I would go for a more standard star type environment. But hey, it's cool. It's going to be awesome.
Before I go on, is this change of volume actually distracting people? Should I just shut off my microphone, or should I just keep it? It's cool? Awesome. So these planets are very far away, and one of the actually most discussed aspects of the film, at least on science bloggers and articles, has been the wormhole that NASA uses to get to these planets. So we have an expert, Julian Sonner, on quantum gravity, on the search for a kind of a unified theory of nature. And one aspect of that, and actually it comes out in the film, what we'll discuss a little bit later, is the how quantum gravity bears on black holes and on wormholes. So Julian, tell me, is the wormhole a realistic thing? And if there were wormholes, could we use them for this kind of transportation network?
Well, so I would say the answer is yes and no. I actually also haven't seen the movie, so I don't know the details of this particular wormhole that they are imagining. But the idea of a wormhole is definitely conceivable. In fact, it's a possibility if we think about the theory of gravity as we understand it now in the shape of Einstein's theory of gravity. And the idea is actually really quite simple. And can be sort of demonstrated. So I can show you how it's done. Well, for that, what you need to understand is that the great idea that Einstein had was that gravity is described by curving space and time. It's hard to swallow, but we can sort of imagine it as let's just think about space, and it's somehow curved. So what a wormhole is really quite simple. It's often, I think, demonstrated like this. But if you have this program here, and you think that actually the space and time that we live in is just this sheet, and you want to get from some point A to some point B, like this, like from here to there, then because you can actually curve space-time, it's imaginable that what you can do is you can bend this such that from our perspective, this point A and B are really close to each other, and then you puncture it, and you actually make a connection between A and B like this, which is very, very, very simple. And what you can see is that the path along the outside is much, much longer than the path along the inside of this. So all it is like using the ability to curve space and time to create a shortcut in this curved space-time. And I just want to say one more thing is that the problem is to be able to get through it. So that's where science and science fiction basically diverge. So I think it's unlikely, I mean, it's my opinion, for example, that it's unlikely that you can create such a connection that has the property that I or you could go through it. But there certainly exist solutions to Einstein's equations, to be technical, which have such a kind of a connection. But they all seem to be of the form where you can't just go through. You'd have to violate some other laws of physics, like you'd have to go faster than the speed of light to be able to go through. But so yes and no in that sense, right?
Always the answer you want to get from an academic is yes and no. So, as I mentioned before in my quick plot summary, NASA sends these kind of advanced parties of astronauts out to assess the habitability of these worlds, and they land on the planet and take measurements and so forth. So coming back to Sarah, would you need to do that? Would you actually need to go to the surface of a planet to assess its habitability, or can you do that by telescopes or some other remote means?
Well, I think certainly most of it can be done remotely, and maybe all of it remotely, and then we might send a probe. I don't think we would ever send a human as like the testing ground. You know? Like stick your finger out in the atmosphere. It's maybe not how it's usually done. So I think we can find a lot of things by just looking at the spectra of these worlds, which Zach is also an expert in. But we can assess things like the temperature of the planet. We can assess what's in the atmosphere. We can assess what the bulk composition is of the planet pretty easily. And actually, we're doing that now for some planets. And we're going to be able to do that for Earth-like planets soon, which is what I'm really excited about. And so I think, you know, we can find a lot of questions, or answer a lot of questions by just using properties that we can observe from Earth without going there. And then if you want maybe, I don't know, to send a microscope to look for little swimming things in the ocean of said planet, send a probe, you know, first, before any humans. So I think most things we can actually do without ever leaving our home planet. But these things are very far away, and unless we have these wormholes, actually sending a probe or anything is going to be, you know, out of our technological, you know, thought process right now.
Cool. And you actually had mentioned Zach, so let's go to Zach.
Sure.
And the kinds of observations that she would need are those things that are being undertaken today?
Yes, absolutely. So Sarah is telling us what we need to look for to find a habitable planet out there in the universe. And the kind of measurement that she wants us to make is to measure a spectrum from a planet. So that's looking at the planet in one way or another and splitting up the light that comes from that planet into lots of different wavelengths, lots of different colors of light. So our eyes are sensitive to 3 colors of light. But astronomers can split light up into many, many more colors. We can split them up into millions of colors, I guess I would say. Yeah, just like fancy displays. And when you look at something with millions of colors, you can see there's just so much more structure that's present there. That you can, and in particular, molecules have kind of spectral fingerprints that exist. So if my eyes could see a million colors, as I look at these fluorescent lights, I would be able to say, oh, that light has magnesium, it has mercury in it, it has a little bit of neon, it has some argon. I'd be able to pick apart all of the elements that are producing light in that fluorescent tube. So when we look at a planet, we can look at its spectrum, just look at the light that comes from it, and learn about what makes it up, what's in it, in particular, what's in its atmosphere. And so the method that I primarily work on is a method called transmission spectroscopy. So this is getting a spectrum of light that filters through a planet's atmosphere. And so the way that I like to think of it is I imagine that there's a person standing on a planet orbiting another star. So this is the planet, I'll be the sun. So, all right, and so there's a person standing on this planet and they're watching sunset. And so they see light that travels from the sun through space and then enters the planet's atmosphere and then enters their eyes and they say, oh, what a pretty sunset. And maybe they say, oh, the sunset's kind of red today. There must be a lot of dust over the ocean. Or they say, oh, the sunset's kind of greenish today. We must be in LA. Who knows? And then but then you can also think about the light that has traveled from the sun through space into the atmosphere and then passes over that person's shoulder, and then goes back out the other side of the planet's atmosphere, and then keeps going and going and going and going for another, I guess, at least 4 years, and then probably 10 or 100 years, and then eventually hits our telescope, hits a telescope that we pointed at that star and watched that planet go in front of the star, and we can measure the color of that light. We can measure its spectrum, and so we can start to pick apart what is in it. And so far, the planets that we've been using this technique on are things that we know aren't habitable. They're so close to their stars, we know they're super hot, they have big, puffy, gas-rich atmospheres, like hydrogen-rich atmospheres, really thick ones. So we know there's nothing living on there. But we've been able to detect a few molecules and a few atoms and learn a little bit about the temperature structure of these planets. And so one of the things that I'm working on, that I think everybody is working on, is trying to find more planets that we can study in detail and learn the kind of things that Sarah wants. Sarah tells us should be there. We just have to go look for it.
Yeah, and along with that, so there's the transiting planet method, but also here at MIT, Sarah Seeger's working on a star shade, which is quite exciting as well, because for a transiting planet, unfortunately there's just fewer a fraction of planets that are going to be transiting for your line of sight. And we expect there to actually be, many more planets around stars near us. So it would be ideal if we could directly detect light from that planet. But that's really hard because a star is about 1 billion times brighter in the visible or 1 million times brighter in the infrared for a sun-like star. And so that means for every billion photons you get from the star, you get one from the planet. I mean, it's quite a technological feat. So what they're doing here at MIT and Sarah Seeger's part of it is this star shade, where you can fly something in front of the telescope, 50,000 miles out or so, and then block the starlight, and then actually directly, to try to, not be overwhelmed with photons from the star, and actually directly detect light from the planet. And the other option is a coronagraph, which is also being developed. So I think with transiting spectra, and eventually with these future technologies in our lifetimes, we should see a star shade or a coronagraph go up into space. We'll be able to see a whole suite of planets and hopefully be able to find evidence of a second origin of life, which is what I find so exciting.
It would be just amazing. So you've seen, or the instruments have seen something like 1,000 sunsets on 1,000 worlds. Have you written a melancholic novel about this?
No, we've seen a few sunsets on a few worlds. So we know of 1,000 worlds. We've only been able to observe the very best ones of them, and so in particular the ones that orbit very small stars are some of the easiest ones to observe. So that's where I've been focusing my work.
Cool. Let's put aside planets just for a moment. We'll come back to it. And talk about another one of the kind of subplots of the film, which is the search for understanding the force of gravity. So Julian, I've actually neglected to identify you as a postdoc at MIT before. This is something you've been working on. So tell us, where do we stand in our understanding of this mysterious force of gravity?
Yeah, so that's to me a really fantastic question. I mean, it's something that really I'm dedicating almost all of my research to. And so I said that we have a theory of gravity. I said we have this general relativity due to Einstein, and that's correct. But we also have other forces out there. So in particular, we have this great intellectual edifice that we call the Standard Model, which basically describes everything that's not gravity. And it's extremely successful, and it's successful because it makes use of what we call quantum field theory, which is just the modern incarnation of quantum mechanics. And so we feel pretty much we can describe everything that's out there using the Standard Model and gravity. The problem is that the Standard Model and gravity don't like each other very much in a profound sense. So sort of irreconcilable differences. And the problem is that what you want to do with a theory is you want to make predictions. So, you want someone to do calculations to say, you do this experiment, it will produce this outcome. That's really the whole point of theoretical physics. Now, you find with the Standard Model that by fixing just a few parameters, you can really predict everything that falls into the purview of the Standard Model. It just works beautifully. And gravity has in itself built in a horrible trap, which is that if you actually want to try and make predictions about processes that happen at incredibly high energies or on incredibly small scales, which are actually, in a sense, equivalent to each other, the theory will require you to make more and more adjustments to it that you somehow need to fix by doing more experiments. And this goes to an extreme where the theory loses all of its predictive power in these circumstances. So it really just doesn't work. There is no way of marrying quantum physics and gravity, at least not any standard way that we know. And so that's where we stand in a sense, and there are some ideas of how to go beyond that. One of them, as you might have heard, is string theory, which is actually what I work on. There are other ideas out there as well, but they basically try to get around this problem by postulating new ways in which gravity could arise, and that's that basically get rid of this fundamental problem that as you go to smaller and smaller scales or larger and larger energies, the quantum theory of Einstein's equations just becomes non-predictive anymore. So it's not a good theory anymore.
Cool, thanks. One of the interesting kind of details that was in the film that struck me was some of the discussion about what is the environment of this black hole beyond the accretion disk. For instance, there's a neutron star that's discussed in the film. So one question I had for you, Leah, was tell us about some of the wacky things that you see around black holes, not just the accretion disk, but the other stuff that's there.
Okay, so the black hole that I'm most familiar with is the black hole at the center of our galaxy. It's a supermassive black hole. It's about 4 million times the mass of our sun. We call it the galactic center because it's the center of our galaxy. And it's about tens of thousands of light years away. And it's a very crowded region. And this is because we're pretty sure that when galaxies form, well, we know that galaxies merge all the time. So two galaxies will hit each other, and when that happens, a lot of the material gets funneled towards the center of the newly merged galaxy. All the stars, a lot of the gas just goes straight to the center. And so the center of our galaxy is sort of where all the oldest stuff is, and it's the most crowded. So again, because it's tens of thousands of light years away, there's a lot of stuff in the way, and I study it in the X-ray. So I'm part of the Chandra X-ray Visionary Project, which is using the Chandra X-ray Observatory, which is a telescope in space, to stare at the galactic center for literally weeks on end. And it's a very crowded field, and we look at it in the X-ray because a lot of the other wavelengths of light get absorbed. I mean, you can also look at it in the infrared, but kind of like Zach was saying, you're thinking about light coming past your shoulder or through your shoulder, and X-rays, they go through your shoulder. I mean, there's not people in the way, but there's lots of gas and dust of other stuff that absorbs.
Not anymore.
So, anyway, so my point is that X-ray is one wavelength regime that's really good to look at the center of our galaxy with. And there's a lot of stuff going on. There's supernova remnants with hot plasma, and so we're not only looking through absorption, but looking at emission from really, really hot gas. There are a lot of neutron stars and pulsars, so these are very compact objects. Again, because there's a lot of old objects, and neutron stars tend to be old because they're formed after stars die. There's a lot of flares and stuff going off from these compact objects. For example, about a year ago, a huge flare came off from what we call a magnetar, which is a highly magnetized neutron star. And at first, everyone thought it was coming from the black hole at the center of our galaxy, and they were super excited. But a few days or a week later, we realized, oh, wait a minute, it's actually just barely just barely offset from it, and it's something else. So we're pretty sure now it's a magnetar. But this stuff there's things going on all the time. So it's a really fun place to study because there's just a lot of stuff. It's a difficult place to study because there's so much emission in the X-ray from these plasmas and a lot of absorption that it's difficult to get a sense for what's real and what's not real. It's difficult to extract, what's a point source and what's not, but it is a really fun and crowded place. So if you were around a black hole like that, you would definitely have a lot of interesting things to see and a lot of interesting phenomena to observe.
So assuming your civilization can last in this environment, it will have a beautiful night sky.
Very beautiful, yeah.
I think this might be a good time to actually open up the floor for questions. I can seed a couple questions if you don't have any, but I'm sure people have a zillion questions. Please.
The way it was portrayed, was it realistic in the movie?
Really, you want to take
I can talk about time dilation, but I can't talk about the movie because I haven't seen it.
We purposely don't want to give any
If you
spoilers.
introduce time dilation, I'll
Because
say
she's
what's
seen
in
the
the
movie
movie.
and she's.
Oh.
All right.
Right. So it's actually I've already mentioned that one of the great things, but also the weird things, is that you should think of space and time as being connected, being they can be transformed into one another. They're really the same thing in according to Einstein. And so you can curve both space and time using energy and mass. So you should really think of a massive object like a star or a black hole, which is somehow the nicest massive object that one can imagine. No, it really is. And in fact, they're extremely simple. They're much simpler to describe than stars, I would say. But at any rate, so it just makes a big old dent in this structure that is space and time. And this dent tells you also locally how time elapses. And it just happens to be the case that it elapses in such a way that if there's a very strong gravitational field that is sourced by a big mass, then time for an object that comes close to this, what we might call it, we call it a gravitational potential. If it goes down this gravitational potential into a region where there are strong gravitational forces, time elapses slower, more slowly than it does for someone who's far away from that big object. And so it's indeed true that if you were to travel to a black hole and come back, then time for you would have passed much slower than it would for me. And this can be measured, by the way. I mean, if you have an object that is not too big, the effect is not terribly large, but if you do a very precise measurement, for example, how time elapses on satellites that orbit the Earth, it elapses slightly differently than it does for us on Earth, and that's caused by the gravitational field of the Earth. So that's definitely a real effect.
Cool.
I'll just say, like, if you're asking about the film, so the effect is real, and we know it happens. It might be a little exaggerated in the film.
Please.
Kip Thorne apparently has done ray tracing and said that if you look through a wormhole, it's like looking at a mirrored sphere like you have in your garden, only you don't see yourself, you see the other end of the black hole, the other end of the wormhole. Is that true? Does the film use that?
Well, I mean, my understanding is that the visualizations in the film were extremely accurate. So I know I trust Kip Thorne. I mean, I don't know how you felt about it as well. He's the one who would do these kind of simulations, so.
I trust Kip Thorne, yeah.
Yeah.
I mean, Kip Thorne also wrote a book about the science of Interstellar, and he goes through and says where they decided to make, for the sake of the plot of the movie, we're going to increase the time dilation. But really, what would the time dilation effect be? And he does that in his book. I actually haven't read it, but it's it's the science of Interstellar, and it came out at the same time as the movie. So if you want to get into like a specific, science of the movie, and not, Kip Thorne did a really detailed analysis, and they made some creative decisions along the way, but they did it with full knowledge, I think.
Can I just say one thing which I picked up on it? Black holes and wormholes are not the same thing, and they're not, necessarily related. So a wormhole, would look different to a black hole. I hope it does in the movie.
Yeah, it does. Questions? Please.
So you said there were 4,875 exoplanets discovered, right?
Good memory.
Couple questions. When was the first one discovered, and did the rate accelerate over the years? And when do you think we're going to discover one like Earth?
Good questions all around. So all very difficult to answer, actually. So the first widely accepted exoplanet was announced in 1995. That was 51 Peg. So that in terms of like discoveries in the universe, that's pretty recent. Just to be fair, there was an object that was discovered in 1989 by Latham et al. That would now be considered a planet, but at the time people didn't consider it a planet because like couldn't possibly be a planet. So you could go back to 89 for that. But then in terms of your other question of is the pace accelerating? Yes. Or there have been big accelerations in the pace at which we have discovered planets. So first, many of the original planets were discovered through the Doppler technique. That means you're measuring the wobble of a star and inferring the presence of a planet tugging on the star. And so that's slow going. And then people started looking for these little dips in light of planets passing in front of their star. And so that started to speed things up a little bit. And then NASA launched the Kepler telescope, which took the numbers from a few hundred to about 4,875, approximately. And so that's just been a huge leap, is Kepler has found most of the planets that we know of. But it'll level off now for a while because we don't have another big mission going up for a few years. But then there's a mission being built here at MIT, TESS, that will find another few thousand more. And then there are other surveys going on that will keep finding more and more. But I think the important thing is not the raw number of planets that we find. It's now finding the closest, easiest to observe, the best planets. That we have enough planets already that we have a statistical sense of what's out there in the universe. And so our goal now is to find the ones that we can really observe in detail. And so that's where people have shifted their focus now. So the number will actually start to slow down, but we'll be finding better and better planets as time goes on. And for your last question about when we'll find Earth, I'm going to defer to Sarah.
Well, he finds the planets, let me just say. But yeah, we found some that are already very similar. It depends on when people, you have to be really careful, especially when you're reading popular science articles, because often they play fast and loose with terms like Earth-like. And when you hear the word Earth-like, do not think that means continents, oceans, and trees. That could just mean it is, the same temperature. Sometimes I've heard that used to for a Jupiter-sized planet that is at the same temperature of Earth, and then they call that Earth-like. Or I've also heard it. Sometimes people will say Earth-sized, and that'll be like literally the size of Earth. We found some planets that are pretty close to exactly the size and density of Earth, but they're very hot. So that's not really Earth-like. That's kind of maybe Hades.
So
Yeah.
Venus,
Yeah.
Venus would be Earth-like. by that
Venus,
definition,
yeah,
right?
for us, Venus would be like terribly Earth-like, and it's nothing like Earth if we were to observe it around another star.
Yeah.
So I think we haven't found an Earth clone yet. We are approaching that, and I hope we will find that soon. We have found planets in the habitable zone, though, that are small enough that they could potentially host life. And so I think that's exciting. So we found planets that are maybe like the big brother and big sister of Earth, and that might be habitable, and that if they were closer, unfortunately, the planets that we found with Kepler are very, very, very far away. We're never going to be able to follow those up. So now this is why we need tests to find, okay, let's see what are the planets close to us.
Mhm.
And the simple reason for that was Kepler was looking at the statistics of planets. We wanted to know what fraction of stars have an Earth-like planet, so we know how many stars do we need to look at to find something that we can follow up with. And so Kepler needed to look very far away at one single patch of sky for the whole time, and so those stars are just too far away for us. And that mission then got these statistics. But now the name of the game is, okay, let's fly something and be looking all over the sky to map it out and find out the planets around us, that we could follow up. And then we can make more declarations on, is it Earth-like? Because we need to know, like right now, Venus would look pretty darn Earth-like to us. But we want to find out things. If we were to probe the atmosphere of Venus, we would quickly see, oh, there's a huge amount of CO2, the pressure is insane, it's not Earth-like. So we need to do follow-up missions with the next generation of telescopes, like the James Webb Space Telescope, which will launch in 2018, to try to actually find something that is Earth-like. So be careful when you hear that term in the news.
Cool, please.
So when you talk about those close to us, how many light years away is close? Because you're seeing them
The
more
nearest
like
star is like 4 light years away.
that close.
Mhm.
So 4 light years, I'm still far away.
It's the
but-
nearest
Pretty
How
far
long
away.
would it take there?
So like Voyager has been traveling for 35
excited.
years, and it's 1 light day away.
Yeah.
So, and the nearest star is 4 light years. So it gives you a little bit of the sense of our technology gap. At the speed of Voyager, which we can go faster now, but still not much faster. At the speed of Voyager, it would take 70,000 years to get to that nearest star. So these stars that we're going to look for are probably within 30, 40, 60 light years, something like that.
Yeah, I would say like less than. So the expert in the world is actually
Courtney.
feeding us answers here. So Courtney Dressing has calculated the statistical rate of occurrence of planets like Earth around the nearest stars. And so what is the number? How far out do we need to go to find a habitable planet?
I'd say within 20.
20 parsecs.
20 parsecs or light years?
20 light years? Holy
That's so
smokes!
close.
Okay, so 20 light years. There you go.
Go start looking, wow.
Around
Around
the M dwarf.
obvious.
Cool. Please.
Yeah, so obviously I shouldn't trust the science of the movie, but it made me wonder something. I saw the movie, and so
No spoilers. Be careful about spoiling. Okay.
well, I mean, just one thing they show is basically a solar system, black holes, the smallest kind of black hole in the solar system. My question is there any conceivable situation where, like, let's say one of the planets is a rocky planet, where there's going to be absolutely both in this kind of scenario with a black hole, very small black hole?
What was the question?
The question is if a rocky planet around a black hole would be cold.
Absolutely cold, yeah. Is
Yeah.
there any situation where that wouldn't be the case? Because obviously in the
Yeah, so as long as there's material falling into the black hole, there will be something that's lighting up. If it's a naked black hole with nothing, yeah, that planet would have no source of energy or light. In the film, that's not the case, right?
With a small black hole, like, would there be enough radiation?
With a, I mean, the distinction between a small and a big black hole almost doesn't matter in that case. It really has to do with how much material is falling in on it. So it has more to do whether or not it has a companion star or a source of gas that's falling in. Because it's the gas around the black hole that's going to be a source of light. Yeah.
I mean, I don't know whether that is the question that you have, but it's true that black holes themselves radiate. I mean, that's this very famous Hawking effect. But that radiation for any macroscopic black hole is so faint that it would, I mean, okay, I don't know the numbers, but I don't know even the numbers you need to have a sustainable planet, but I can tell you with certainty that it's many orders of magnitude lower than that. If you have a very small black hole, it does in fact radiate a lot. In fact, it explodes. But it's first of all, it's a very small black hole, and the explosion is very violent. So that's also not something you could survive.
Just to chime in, there's also in the exoplanet community, people have also thought about planets where you don't necessarily need light heating you. And so the idea here is there are some, as you go to smaller and smaller stars, eventually stars stop being stars. We call them brown dwarfs. So they don't emit a lot of light at all. But you could still imagine something orbiting around a brown dwarf. But one problem is it might be very cold, right? Because there's not light keeping you warm. But if you're close into a star, then the tidal forces, the fact that you have something with very strong gravity, takes your planet and like stretches it and squishes it and stretches it and squishes it. And in the same way that, if you take a rubber band and you do that, it heats up. So you could have, I have no idea. Again, I'm glad I didn't see the movie, so I'm not giving anything away.
But it would be very volcanic and interesting, wouldn't it? 'Cause
yeah, it'd be crazy.
Io, which is one of the Io, one of the moons around Jupiter.
Yeah.
Right, is very volcanic, and the reason it's like that, it's a very, very teeny tiny moon, but it's so close to Jupiter that it gets squished a lot. So it's got a lot of thermal activity going on because the rocks are getting squished and molten.
Right.
Actually, one fun thing about black holes is that somehow the bigger they are, the more massive they are, the nicer their environment is from the point of view of gravity. So it's generally also a fact that the horizon, what people call the horizon of a black hole, like the boundary from which light cannot escape, is actually not a special place at all. If you pass it, you wouldn't really be able to tell, unless the tidal forces are so large that you get torn apart. But those tidal forces tend to be smaller at the horizon of a larger black hole. So the larger the black hole, actually, the more likely that you'd survive being near it, which is somehow fun, I think.
Back there, I think.
I haven't actually watched the movie, but my question is, do they ever agonize about planetary protection, or is it just like, humans are ready to die and we don't care anymore? There's nothing about the sun, we're going to kill it by arriving with our microbes?
It's a good question, but I think it falls into the category of spoiler to answer that particular question. Do you think? Those who have seen the movie on the panel, should we?
So again, I haven't seen it, but I'll try to answer your question. Maybe that's also the problem. So the idea here of planetary protection is something that NASA has to take seriously, particularly as so exoplanet people, we don't really have to worry about it because we're looking and not touching at all of our planets. But in the solar system, we are, we're poking at stuff, right? And so it's a big issue of making sure, if you send a robot to Mars or send a robot to an icy moon, to Europa, you want to make darn sure that you're not sending microbes with it as well that will then take over that planet. So it's something that we need to be concerned about.
Oh, I've never thought about that.
Right?
It's a big part of the budget, actually,
Yeah.
I think. Yeah.
Cool. And over here, and now come over here.
Yeah, I'm an MBA student, so hopefully this is quite easy.
Wow, with an introduction like that. It's going to be a really good question.
So in the movie there were some frozen clouds that were kind of hanging in the air. How is that possible due to low gravity?
Frozen?
Well, we do have ice clouds on Earth. I mean, I don't know what, I haven't
Are
seen
they
the
like
movie either.
frozen solid?
They're ice particle clouds. The highest, so we have water clouds, that you go through with your plane. and stuff, and when you see them, they're like the nice fluffy things. But then as you go farther up, there's ice clouds in Earth's atmosphere. I haven't seen the movie. I'm not really sure if I can comment on the precise nature of these, like if they're like solid blocks of ice.
Yeah.
Well, I don't know about solid blocks of ice.
It's a pretty dramatic scene, so that was one of the times I said, oh, I think I'll give the filmmakers that because it was worth it just to see the ice cloud up there.
Sure.
There's a question over here, please.
Yeah, I guess I was going to ask a question to experts in black holes. So there was like this recent a viral article research paper in Facebook where they were saying that the universe is going to start a Big Bang, but it's actually like a black hole, and that the whole universe is in a black hole. You probably heard of this about this theory. And like I was asking like friends around, and is that even conceivable that the universe we live in is actually exactly a black hole?
So let me answer the last part of your question because the first part I acoustically didn't quite understand. So it is in fact possible that we're right now inside a black hole.
Should I be worried?
I can elaborate a bit further. Please.
Show me.
It's it actually turns out that one of the most counterintuitive things about black holes or gravity in general is that whether we're inside a black hole now actually depends on things that happen in the future. So
It's getting better.
That's actually just true. But the particular thing that has to happen for us to be now inside a black hole is that somehow in the future, like a large shell of mass collapses somewhere from the outside and collapses into this region of space. And it turns out that a black hole really is by definition the region of space and time from which you cannot escape out to a far region from the black hole. And because the gravitational pull, I mean, it'll take us a long time to travel anyway. And by the time we're on our way, the pull of this shell that is collapsing in the future is actually so strong that it'll prevent us from escaping from this region. It's something that people call the teleological nature of black holes. You need to know the entire history of the universe if you want to decide whether you're actually inside a black hole or not. So yeah, but that I didn't understand the first part of your question.
Have I missed any questions behind me? Please.
Sorry, I'm a Sloan fellow, so the NBA seems good. So you mentioned you're looking for life in Earth-like planets. And then you also mentioned Io. Io is not different than a volcano on Earth, and we find life in a volcano on Earth. Wouldn't it be easier to start looking at it from the easy perspective and then branch out? Because as you mentioned, Venus could look Earth-like and not have anything.
Yeah, so I think this is another key. I'm so glad you asked this. This is another key point. So there are two types of life searches. There's a search for life in our outer solar system, where we're going to look at a much more diverse body of objects, such as Europa, Titan, especially. And those would have, especially Titan has these liquid methane lakes. The type of chemistry that would happen there and the type of life that we would expect to be there would be entirely different than what we have. But that is, we cannot even tell if these planets have life, and we're so close to them that we're never going to be able to tell around another star. So when we talk about looking for life around other stars, we're looking at the remotely detectable habitable zone and the remotely detectable signs of life. And that's very different than where life could be, because we know on Earth you see life in the deepest underground ocean vents, but can you see that from another star system? No. We know you can have life in very cold, icy environments. We know you can have life, pretty much everywhere on Earth. So I think microbial life especially can exist in, so many environments in the universe. But we're never going to be able to detect that from Earth. We need something that's interacting with an atmosphere and that's in a large enough abundance. For example, look at Mars. It's fairly habitable, but again, we can't tell if there's life remotely there from Earth. because there's not enough of a biosphere producing enough of an atmosphere that we can detect, and even when we go there and look in the soil, it's difficult. So I think you have to be very careful when you hear the word habitable zone. There's often I hear like people say, oh, push, we have like, you know, Europa could be habitable, all these other things could be habitable. Why isn't the habitable zone everywhere? What we're really neglecting the word is the remotely detectable habitable zone. And that gets to be a mouthful, but really that's what we're interested in. What can we recognize? And because life on Earth really relies on water, very fundamentally, and then also it uses CO2 a lot. We see water and CO2 everywhere in the universe, so there's no reason to think that, you know, life somewhere else didn't happen to use that. And because we don't have a full understanding yet of even, you know, alternative biochemistries that could exist and what kind of biosignatures would those be, we're kind of out of our element. What would be a biosignature around a Jupiter-like planet? We don't know because we don't have any idea of that. But we know what biosignatures Earth-like type life creates, and that's where we're going to go first because there's about, you know, 40 billion habitable planets in our galaxy, you know, based on our statistics. And of course, you know, hopefully within 20 light years, we'll have one that we can remotely access and look at.
Well, the organizers really put the fear of God into me about ending on time because people have to be able to get up to Davis Square for the film. But I think the speakers will have some time to stay afterwards before they have to go up to the film. Did you want to say something?
Yeah, I just wanted to kind of throw this in as a sort of wrap up. So Interstellar is kind of like capturing our imagination, you know, it taps into something. You guys are all studying things that are just so far out there, you know, exoplanets, 20 light years away from Earth. I wanted to kind of end with each one of you kind of discussing a little bit about how your research fits in with our understanding of our place in the universe, and maybe discussing why you think this is such a sort of interesting field for you to pursue as scientists, and you know, what might strike a chord with the kind of public imagination.
Do you want to go first and then we'll go down the road?
Sure.
We could flip a coin.
No, this is fair. Yeah, so one of the reasons I love science fiction movies is that it's, you know, it's this imagining of what could be out there. And so that's kind of the same thing that I like about my research is we're kind of trying to discover what's out there. And so particularly in the field of exoplanetary science, where we've gone from having 0 planets outside our solar system in 1989 to what we now know of, this huge diversity of worlds and the kinds of observations that we can make of them, to really go for a select few of these planets beyond just the fact that a planet exists, to try to like piece together a story about what that planet is. So, you know, measuring its size, understanding its orbit, measuring its mass, figuring out its composition, studying its atmosphere. There's just a lot left to figure out in the universe, and so it's cool that this is a field where we're starting to do this, and we're building telescopes that have the capabilities to really, I think, for me, the exciting thing is to empirically address the question of that Sarah mentioned before, of is there life out there somewhere else in the universe? We've always had to wonder that until, you know, 10 years from now. So, and maybe in 10 years from now we'll still be wondering. That's pretty likely. But we're building the telescopes, and we're finally starting to do the things where we can really use science to ask these really science fiction questions, or answer these science fiction questions.
Cool. Okay, so one of the reasons I'm studying the Galactic Center is actually to use it as a probe to study stuff that's in between us and the Galactic Center. And what I did my thesis work on, and what I also find incredibly interesting, is dust. So we want to know, like, what's going on with the gas and dust in between us and the Galactic Center. And in general, I think dust is amazing because it's where a lot of the heavy metals are. They're kind of like the seeds for what's going to eventually grow planets. And it's what's going to deliver all the heavy metals that form you and me. So for me, it's trying to understand, you know, how we got from mostly hydrogen and helium to delivering chemicals and having interface for chemicals and creating planets and eventually getting to us. So that's I guess how my research would kind of connect to this question of life in science fiction.
Yeah, so I'm interested in remotely detecting life on another planet. So just answering this question of, are we alone in the universe? We all have our opinion. We don't have any data. So that's what I would really like to answer in my lifetime, and why I do the work I do. And it ties in with Zach, and so we both are interested in the same thing. I do more theoretical modeling of how good of a biosignature is that going to be. Can we test? Is there false positives there? Is that a robust biosignature? But it's all steps along the way, as well as we're very interested in dust grain chemistry, delivering things to planets. So it's all ties together.
Well, so I think my field of research is in a sense different, although some of the objects we talk about are the same. So I get up in the morning because I want to understand gravity, and from like a theoretical point of view, because we know theoretically that it doesn't actually work so well as a quantum theory. And well, I briefly described why that's a problem, but you might think that it's an academic problem. It's somehow like, why shouldn't these two get on together? That's really no problem. I mean, maybe it bothers him, it shouldn't bother me. Actually, there are things that we can't answer because of this problem. We don't know what happened at the beginning of the universe, because in order to understand what happened, or even if there was a beginning of the universe, to answer that question, we need to understand quantum gravity. We need to understand what happens at a Planck time. We need to understand what happens in a Planck length, and so on and so forth. So these are not academic questions. These are really questions that relate to real physics, and in fact lead to physics that we might even at some point be able to observe. Actually, this is why people like me now are interested in dust, because we thought that we saw signatures from the earliest period of the universe, which will tell us about quantum gravity, but what we actually saw was dust. So we need to understand what dust is there in order to get to the stuff that's before, right? So yeah, so that's what I want to, I want to understand basically gravity in extreme situations, such as at the beginning or not beginning of the universe.
And just to maybe try to answer your question as well, one reason we watch science fiction films, at least one reason I enjoy them so much, is that it helps to reflect on our own condition. And obviously I think that's why the Nolans were so interested in this particular film that I hope you go see tonight or some other time. And I think that to understand where we are, we need to understand what other possibilities there are and where we fit into that broader realm of possibility. In a past life, I studied Venus, which came up a little bit earlier. And it's amazing. It's a hell of a old planet, but it's so much like our planet. Why? It's the wayward sister. What happened to send Earth and Venus onto two different trajectories? And that might help us take care of our own planet better. So that's how I might answer that question. Let's really thank the speakers. They've done such a great job.